And it's joint work with Cornelia Drutu and Frederick Haglund. So, yeah, let's just first recall this something that people might know that might be maybe more classical is Serre's property Fa, which is that you say that a group has property Fa if any action, let's say simplicial action, on a tree has a fixed point. And it's well known. In fact, I forgot to look up who I should attribute that to. Maybe somebody in the audience knows. That if a group has property T, then in particular you have property Fa. But the converse is not true. Oh, those chalks are horrible. Are there little stones in it? Converse not true. And in fact, you have some example. The Coxeter group given by G, A, B, C, such that, okay, A squared is B squared is C squared is AB cubed is BC cubed is CA cubed. This group, this is this guy. This, what? It's not this guy? Well, this, come on, it's this guy, whatever. Okay, no, it's this guy. You happy? Okay, so this has property Fa, but not property T. So it means that the converse is not true, so you might wonder what is the right converse? What is the right object that's going to give you property T if any action on it has some kind of a fixed point? So we didn't get the fixed point, but yeah. So the question that brings me is what should be a notion a higher dimensional tree? So the answer is the notion of median space that I will explain. And before explaining the notion of median space, I'll put up the theorem that actually motivates the stock, which is a theorem in collaboration with Drutu and Haglund, and which says that if you have G locally compact second countable, if you like, you can replace that by discrete. Then it has property T if and only if any action on a median space has a bounded orbit. So the plan for this stock, before I give the plan for this stock, let me just mention that this direction kind of was already there by, I think, Niblo, maybe Niblo Reeves, and maybe it was in Roller's unpublished habilitations thesis, and it was definitely, for the discrete case, in Nika's master thesis. And as a corollary for this theorem, we get another characterization of property T, which is that a group has property T if and only if any action on an L1 space has a bounded orbit. That's a characterization that has been independently obtained by Bader, Furman, Gallender, and Monod in a paper where they study action on LP spaces. So the plan for this talk is to start by talking about median spaces. Then I'll talk a little bit about property T. And then I'll give you a few random ingredients from the proof. So it's not going to be a proof. Okay. So, yeah, just a comment about property T. Of course, if you don't know what property T is, you can take that as a definition, but it's not the original definition. But I'll talk about property T in the second part. So maybe I'm not going to make the comment right now. Oh, yes, I will make the comment. So even though it was not introduced as such, property T can be thought about as a measure of complexity for a group. And it has been a common pattern to show that property T groups cannot act on this nice space, this other nice space, this other guy. And that has been recurrent work by many people. For instance, Sherix, Martin Valette, Robertson, Steger, Navas, and maybe I'm sure I'm forgetting a bunch of people. But it's a recurrent pattern to say, okay, you have a group of property T, then it cannot decompose as a free product or an amalgamated product. It cannot act in many spaces, et cetera, et cetera. Okay, so let me just go to the median space part. So what is a median space? So before giving the definition of a median space, I'm going to start with a metric space, and I'm going to suppose that it's geodesic, meaning that for any 2 points, you can find a geodesic between those 2 points, meaning a path such that gamma 0 is x and gamma d is y, and this is an isometry. Okay, and then for a metric space, you're going to say that a point T is in between x and y. Oh, wow. Those are good. Yeah, if the distance between x and t plus the distance between t and y is equal to the distance between x and y. And so you're going to denote by the interval between x and y the set of t's and x that are between x and y. So, right. And is there an eraser? So far, I have the notion of a geodesic metric space and the notion of being in between. And for 3 points x, y, z, a median point is any point m that's in between x and y, in between y and z, and in between z and x. And you will say that x is a median space if for any 3 points you have exactly a unique median point. So there are two things, existence of a median and unicity. And both are really important, as we might see later. Okay, so I should give you examples. So So the first example is the real line. The real line with the Euclidean distance. If you have 3 points, now I should quiz the audience. What is the median? Whoa. Check that, so y is definitely in between x and z, and y is actually in between y and z, so this is going to be the median. So let's go to an example that's a little bit more interesting. And it's the notion, it's a tree. So if you have a tree, it's kind of visually obvious that the median is going to be this point. In fact, each time you have 3 points in a tree, one of the geodesics is covered by the 2 other geodesics, and the median is this point here in the middle. So this is going to be the median. And so more interesting, so yeah, since I was promising a higher dimensional version of trees, I cannot stop here, and I'm going to give you R2 with the L1 norm. So what is the L1 norm? The distance between x1, x2, and y1, y2 is given by x1 minus y1 plus x2 minus y2. And that's if you have a point x and a point y. The interval between x and y is given by the square. And that's the interval between x and y. And so if you have 3 points, your third point is here, your interval is here, and your last interval is here, so you can see that the unique intersection point is this median here. And so in fact, more generally, so R2 with the L1 norm is just the product of R with the sum of the 2 metrics. So more generally, the product of median spaces x1 plus x2 with the sum of the metrics is again median. And the median of 3 points is going to have 2 coordinates. And both coordinates are the projections of, are the medians of the projection of the 3 points. And in fact, more general, I'm going to erase the plan. That way, if I don't stick to the plan, you might forget what I said, that there will be 3 parts in my talk. Okay, yeah, another example is if you have a measure space, W mu, then L1 of W mu is going to be a median space. So let's pretend for a while that in L1 of W mu functions are continuous. The median of 3 functions, the median of 3 continuous functions, then you can evaluate that in a point. That's going to be the median of the 3 evaluations. So then, yeah, you can see that all continuous functions have medians, and by approximation, you'll find medians for L1 functions. So because of this, you have product of trees, and you have also cat-0 cube complexes that I will not really define. So Cat0 cube complex, I'll just wave my hands to explain what it is. You take a bunch of Euclidean cubes and you glue them together isometrically along subcubes. And you do it in such a way that you never have, if you have something like this, it means that you will have the full cube in there. So in words, it means that the link at each vertex is a flat complex. And a flat complex is a simplicial complex so that each time you see the n skeleton, each time you see the n skeleton of a simplex, the simplex is actually there. If you see if you see one skeleton of an n simplex, the n simplex is actually there. And so, in fact, the zero skeleton of a Cat0 cube complex with the one skeleton metric is a median space. And in fact, there is a notion of median graph, which is, it's a graph so that the zero skeleton with the one skeleton metric is a median space. And it's a result by Chepoy that all median graphs are skeletons of Cat0 cube complexes. Okay, so I've given you a few examples, but in fact, the example I'm going to give now is the example. Yeah, I'm going to leave this definition on. So the example I'm giving you now was in some sense, to me, it was in some sense disappointing because I thought that, initially I thought that median spaces were to Cat0 cube complexes what R trees are to simplicial trees. So I thought there were just some non-discrete generalization of Cat0 cube complexes, but I think that in fact it's a little more general than that. So this is a crucial example. The crucial example is the following. You take X a set, B a sigma algebra of subset, and mu a measure on B. So just a measure space. And then you take a subset of X, and you look at BA0, which is the subset such that the symmetric difference with this fixed set A0 is measurable and has finite measure. So that's a set of subsets. And on that, you can put a measure. A distance, a pseudo distance. And so the pseudo distance between two sets B and C is just going to be given by the symmetric difference between B and C. And you can check that this is a pseudo distance. This is a pseudo distance. And you define B naught. I should just curl it. B naught as to be this BA0 that you mod out by sets that are a pseudo distance equal to 0. So just the standard way you have a pseudometric space, you mod out elements at distance 0 to get a metric space. And yeah, so now we have a metric space, and I claim that this is a median space. And not only that's a median space, but we'll see later that any median space embeds in such, isometrically embeds in this type of median space. Yes. Yes, indeed. Right, so that's a metric space, and I claim that it's a median space. So first, what is the interval between two elements? So the interval between two elements is the set of D's in this B naught such that the intersection is contained in D and is contained in the union. That's going to be the interval that goes, that's going to be all the points that goes from one to the other. And so the triangle inequality follows from the fact that the symmetric difference of A with B, symmetric difference of A with C, that's just a formula for symmetric differences. That gives you the triangle inequality, and the median between 3 points ABC, the median between 3 points ABC is A union B intersection B union C intersection C union A. So yeah, basically for this picture, here you have B and C. You go from B to C. The geodesic is just going to slowly displace this set to the other. And here, if you have three sets, your median is this guy here. Okay? Oh, the mic is still there. Okay, yeah, so the remark that Mark made is that, in fact, D0D embeds in L1 of X mu isometrically. Okay, right. Let me now spend make a little digression on property T. Small digression on property T. Yeah, it's part 2, that's right. I'm going to digress to part 2. So that's Duke-Kasdan. When was his paper? 70s, right?
68.
68. Thanks. So I think the original definition is that the trivial representation is isolated in the unitary dual for the Fell topology. But in fact, I usually use, an equivalent characterization, Guichardet, due to Delorme and Guichardet, says that G has T if and only if any isometric action on our Hilbert space has a fixed point. So for median spaces, we cannot hope for a fixed point because you have median spaces that, if you take 4 points, or if you take 2 points only, that's a median space. And so you can act, Z mod 2Z can act without a fixed point, so that has property T. Anyway. Right. basic examples of property T groups are S ln R, S ln Z for n greater or equal to 3, S ln QP, SP and 1, compact groups, not Z and F2 or Fn, and so not, and so those one have property T, and you have also a quotient of T groups. So all the quotients of the guys here, and they're very far from amenable, meaning that property T groups that are amenable are automatically compact. And another, oh yeah, so I think the first in Kasdan's paper, what he showed is that if you have a property T group, it's finitely generated. A discrete property T group is finitely generated. In fact, if you have a locally compact second countable group, it's going to be compactly generated. And let me just mention a result that goes along the lines of the measure of complexity for property T groups, is a result that due to Olshansky that says that any finitely generated group, so think about the most horrible finitely generated group you can think of. Well, you can find a property T group in which it embeds. So that's, yeah, that's what he does. That's what he does. In fact, he shows that Gromov hyperbolic groups is SQ universal, and SQ universal means exactly that. You take any group, you can embed it in a quotient, and then you just have to use the SP and 1, for instance, as property T. Okay, so that was the short part 2 of my talk. So now, before giving you part 3, I'm going to give you a small exercise, which is the following. If you have R2 with a Euclidean norm, well, you can embed it isometrically in L1 of 0, 1. And how do you do that? You take xy and you map it to x sine t plus y cosine t, maybe with some constant somewhere, square root of something. You can figure out what is the constant. Anyway, so why did I say that? Well, because here's a median space, and here is something that is absolutely not median, but it's almost a Hilbert space. If it was complex, it would be a Hilbert space. Right. So here's something that we saw is median, and here's something that you can actually show very easily is not median, because you take a triangle. The interval between 2 points is only this line, so there's never an intersection between 3 intervals. Okay, so that's the little exercise to say what is that, to say that there is a bunch of metric spaces that are not median, but that still isometrically embed in a median space. We'll see in the end of the talk that there are spaces that absolutely do not embed in a median space. Okay, so let me just go to now telling you about random ingredients of the proof. So one ingredient of the proof is the notion of space with walls. Is a set X with a bunch of subsets that H has to be closed under taking complement. And you're going to take W, which is the set of walls, and those are going to be sets of the type H complement, so that's H is in H. And you want also be a sigma algebra of subsets of W, and mu a measure on W, and you want, so that you can always do. So far I haven't said anything. That you can do with any set. So to have a measured wall space structure, you need something else, which is, so that's the end of the definition. So you need something else. You need that for any x, y in X, W of x, y, so that's the set I'm going to define. So those are the set of walls that separate x from y, such that, so H, x is in H, and y is in H complement. So you want that this set here to be measurable and have finite measure. So, yeah. Let me give you a few examples of what is a space. Yeah, so wall spaces were, as a discrete wall spaces were introduced by Haglund and Paulin, and then Cherix, Martin, Valette formalized the notion of measured wall space, although Robertson and Steger had already used measured wall space without calling them measured wall space. And in fact, Sagid has already used wall space without calling them wall space. So anyway, that's life and math. What did I want to say now? Oh yeah, I wanted to give you some examples of wall spaces. So one example is are vertices of trees. So the set of walls correspond to the set of edges. In fact, each time you remove an edge, you really separate your vertices in two sets. And between any two vertices, you have finally many edges. So that's the measure you get is now just the counting measure. Or you also have Z2 that you think as a grid like this, and your walls are going to be just separating left to right. You have two families of walls, the vertical one and the horizontal ones. And more generally, you have cat0 cube complexes. So cat0 cube complex, even though I haven't given you a formal definition, something like this. So that's see what I'm doing. If you keep going, that's in fact a cat-zero cube complex on which PSL2Z acts probably and co-compactly. So the walls are going to be hyperplane, where you actually take an edge and you cut perpendicularly like this, and you keep cutting until you don't have anything. So Sagiv defines them as saturated equivalence classes of edges. That really allows you, so those are really walls you separate your space into. Another example would be this. Here you can really see the walls. And this is actually the system that gives you the cluster group that I give you in the beginning. And so since I was giving you random... Sorry? Yeah, maybe it's wrong. The exercise is to fix it. Fix that. The exercise is to find the right embedding. Really? You integrate between 0 and 1. Huh. You want that? Maybe that's better. I don't know. No, maybe not. Let me just not. Yeah, Mark, that's your task. You're going to fix that. Okay, so I've given you the notion of wall spaces and the notion of median spaces. And in fact, one theorem that comes in that is a middle step to prove the theorem I put in the beginning, which was that a group has property T if and only if any action in the median space has a bounded orbit. A middle step is the following, is that any wall space isometrically embeds in a median space. And the other theorem is that, the other part of the theorem is that any median space has a structure of measured wall space. Yeah, so you kind of should complain here, because a wall space was this set with a bunch of walls, and I didn't put any metric in it. But if you have a wall space, since you have this thing here, which tells you that the measure between any 2 points, the measure of the set of walls separating any 2 points is finite, you can decide that this is going to be the distance between x and y. That's not a metric. It's not a distance. It's a pseudo distance, and you do the way you do it as usual. You take the pseudo distance mod out by elements at distance 0, and you get a metric space. So a space with a wall space, in fact, gets more or less a metric. And for this metric, it isometrically embeds in a median space. And yeah, so this part one, this part here of this part one of the theorem that's the idea of the proof was already in Micah Sagiv's paper on cat-zero cube complexes in hyperplanes, but he didn't spell it out very clearly. So Graham Nibel and I, some years later, wrote a paper explaining with the language of cat-zero cube complexes and wall spaces how, when you have a space with wall, that's not a measured wall, that's really discrete walls, a counting measure, then you can embed it into a cat-zero cube complex. And the way you do it, the points in the median space are sections from W to H. You have a natural projection that goes from H to W, which consists, you take a half space and you associate to it the wall. And in fact, this map has a bunch of sections, which is you take a wall and you have to pick one of the two half spaces. And in fact, if you're in a space with a wall, you can see that here, if you have a point in your tree, that determines a section for half space, for walls to half spaces, because you just choose the half space that contains this point. But that shows also that the median space can be much bigger than the space with walls. And so for the second part, for the second point, that was a really tricky point. You have a median space and you have to put a structure of walls. And so, but that's, okay, so before telling you about the second point, let me just give you the definition of a convex set. So C in X is convex if it's strongly convex, meaning, so for today, it's going to be if for any x, y in C, then the whole interval between x and y is totally contained in C. So, as an example, if you're in R2 with the L1 norm, this, for instance, this guy here is not convex, because if you take 2 point here, then the interval is here and it spills over. And yeah, so to prove point 2, what you do is, well, that's where I thought that the story was interesting. We initially actually initially what we did is we found, given 2 point, we explicitly constructed a wall separating those 2 points. And there's a messy construction. And then we noticed that Schollander, and I think it's in 54, showed that for any x and y in a median space, there exists a convex wall such that, so H and H complement are convex, and X is in H, Y is in H complement. So apparently, in the 50s, there was a notion of median algebra, which was a set with what people call the Ternary Operation. And those were studied. And I have to say, I looked at the paper and I didn't understand much. But since we had another way of doing it, I didn't really bother. And they were doing everything in a very algebraic and abstract way, but median spaces, as in metric spaces with this property, are particular cases of those median algebra that those people were studying in the 50s. So see, this is math. You think you're doing something new, and people have done that 60 years ago. Okay. So yeah, so then what do you do? So yeah, I was explaining how you have a median space, you want to put a structure of measured wall space. Well, you do exactly the same thing as you do when you construct the Lebesgue measure on the real line, starting with intervals. So, so then you set W of x, y as the set of walls separating x from y, actually convex walls. We know that there is at least one due to Schollander. And you also set the measure of x, y, of W of x, y, as to define this measure as to be the distance between x and y. You have a metric space, so you can do that. And then, so those are your intervals, and then you extend your intervals to a sigma algebra in the same way you do it, in the same way you would define the Lebesgue measure on the real line, using what? Carré-Doray's extension theorem. Okay. Oh yeah. Let me just give you an example illustrating one. So yeah. So I said that any wall space isometrically embeds in a median space. If you think of R2, you have several wall space structure that you can put on R2. So one thing that you could do is you take those walls. So the median space you get then is actually nothing more than R2 itself. This construction will just give you R2 with now the Euclidean norm. Now if you add some walls, if you add one direction, then you start getting R3. Then this construction will give you R3. And if you take R2 with all possible walls, with all possible lines, and you define between any 2 points, you define the measure of the wall separating those 2 points as to be the distance between those two, the Euclidean distance, then the median space that you get is exactly it's some infinite dimensional thing. And another example, another nice example. So another nice example is Hn, the hyperbolic n space. So that is a measured wall space. The walls are the Hn minus 1s, and you have tons of those, right? Here I drew some, but anyway. Yeah. But in fact, one thing that we prove, although I don't think it's in our paper, it's maybe in a paper that might arrive in a few years, is that if you have, if X is a Gromov hyperbolic wall space, then X embeds isometrically in W, that's a median, at finite Hausdorff distance. Which which is definitely not true. For instance, if you take this picture, the wall space you get, you actually embed it in R3 as some diagonal hyperplane. And I guess that in the minutes remaining, I'm just going to give you the idea of proof that G has T if and only if any action on a median space has a bounded orbit. So to do that, you use a characterization of Robertson and Steger. And they say that if gamma is countable, then you have property T if and only if any measure definite kernel invariant is bounded. And what is the notion of measure definite kernel? So a measure definite kernel is a kernel, so it goes from x cross x to R. And it's a kernel that factors through some measure space. You have a map F, and you want that phi of xy is the symmetric difference between f of x and f of y, where f from x to b is a map, and b mu is a measure space. And so, yeah, so using this characterization and what I just told you, we introduced the notion of median definite kernels, and also the point is that median space behave very well taking limits, so we can extend the discreteness to any locally compact second countable group. So I'm going to stop here. Thank you very much.
Any questions?
Complex hyper, no, they don't. Yeah. No, we've been trying and failing. Yeah, yeah, because those already they don't have a wall space structure, because you know the n-1 dimensional thing, you don't really know what those are. So yeah, we would like to know, but we don't. Oh, thanks. Thank you very much.